we're very happy to have Professor Aluffi again. Sadly, this is the last of the sequence of lecture. So I'd like first to thank Professor Aluffi and Professor Teissier again.
Okay.
So Paolo finished with a bang.
Not sure. What I know is that I'm half through my notes and I have 1/3 of the time, so I don't know what will happen. I will have to sacrifice something here and there. But these are very simple-minded things, but they are cute, and I want to at least make the point they're cute. Here's a computation. So let's see if you buy this. So here's another property you can prove about this notation. It's a fact. It's an exercise. It's a nice little exercise. Take the Chern class of L, this line boundary we are talking about, a power of that, and cap with A tensor L. What C is some number. The fact is that this is, can you guess? It's independent of L. Oops, that's my phone. Yeah, let me silence this. And now I'm getting nervous because this isn't quite right. I forgot half of the sentence. The term of dimension C in this is independent of L. Sorry. That would be a little too too much, right? Maybe I should get caffeinated coffee, not decaffeinated coffee. But
it's not too late.
that's true. Why is this cute? I don't want to disturb that board because that's my general goal, but let me show the kind of things I end up doing. I know this is a kind of very simple-minded. Maybe I should sacrifice this board so I don't have to squeeze everything here. But remember, this will come back. This is, in fact, maybe I'll put it here. This is something we want to be able to write differently. And one of you pointed out that it's more readable if you actually single this out as a parenthesis. This is 1 plus. I use that kind of trick all the time. I don't know why you don't. It's suppose that you're doing some computation, maybe some enumerative computation, whatever, and you need the coefficient, of h to the c. This is a contrived example, of course, but it looks like the kind of things that I find myself doing often. So why? I don't care. You just need this coefficient. Suppose you need this. And you can very well tell me that there's absolutely no problem in doing this. This is, in fact, I have to copy it from my notes because my IQ drops by 100 points when I'm at the board, but this is what you do. After all, this is a 3 plus c binomial I times 4 to the I. So far, I'm doing well. And on a good day, I remember the coefficients that you need for 1 over 1 plus something. And in this case, it turns out to be 3 plus c minus I. Choose 3, and then you have to multiply by minus 3 to the c minus I. Why am I not happy with this? Now, this is perfectly fine. David is frowning.
No, it's fine.
Okay.
You said you need the coefficient. I was actually looking for an h of c.
But I have the
there, but you
coefficient.
said
Right?
you need the coefficient. I found for a split second you saw it.
Since I forgot it over there, I might copy it. Yeah. What's wrong with this? Nothing is wrong. So, quick. What is the coefficient of h squared? What is it if c equals 2? And this is going to be an annoying computation. Then you have to start your maple or trust yourself in computing binomial coefficients. So, but we know this. Now, there's this fact. What does that have to do with this kind of computation? Well, you should think of this as maybe the Chern class of the line bundle O4H. If you tensor a line bundle, the effect is simply to change this Chern class by an additive term. So let me rewrite the same thing so that it looks like that. So the coefficient, let me not forget, coefficient of h to the power c in, I'm just going to write it as, so that it looks like that. 1 plus 4h, think of this c of L to the c minus 1, and then 1 plus 4h to the fourth, because I need a 3 plus c, divided by 1 plus 3h to the fourth. So this is by the fact. Now you have choice. You can, this is independent of L, which means that you can tensor by L, your favorite L. For example, you can tensor by O of negative 4. The effect of that would be to take negative 4 out here, here, and here. So I promise, that fact promises that this is the same coefficient. And this is very easy, right? This is the coefficient of h to the c in, everything is gone, right? I have 1 over 1 minus h to the fourth. And again, on a good day, I can remember that this is c plus 3, choose 3. That's no problem, right? So what this is I suppose, a proof of a binomial identity that this equals that. But you don't have to remember the identity. The machine will remember it for you. And I promise, this has saved me zillions of hours over the years, because if you run into this, then you have to work and look something up and whatever, and good luck with that. Well, this. So the freedom that you have by changing this L really allows you to do this kind of computations very efficiently, I promise.
Can you prove by combinatorial identities to intersection theory?
I'm not sure that this is intersection theory. This is the Aluffi calculus, as Boyo calls it. No, but it's a totally mindless manipulation. Yeah, this is easy from this kind of stuff. But yeah, it contains binomial identities, and sometimes you run into. There's a recent paper on Invenciones where there's 2 pages of binomial identities that you can really bypass very easily. So this in my plan was here for a purpose, but I just wanted to advertise that this notation has some application that really make my life easier when I do some computation. But I had a different goal. I wanted to attack something with this. I keep pacing back and forth. I hope this is not bad. This is my goal, to understand how to write this differently. And this is the template for that computation. In fact, let me just write it out. This will be mindless computations. You can tell maybe from there that I have a bunch of fractions. Now this is really... But keep this notation in mind. The notation has disappeared, so I cannot keep it in mind. In particular, what I had is A given as a sum of components. Sorry. Then A tensor I stands for summation A to the I over CL to the I. It's good to keep it in mind, but what I want to use is these properties. If you have these properties in mind, what do you do here? Yes, what do you do here? There's different ways to approach this, but you can think of this as a divisor class divided by a churn class of a line bundle. And that's matching my definition, right? I have something codimension 1 divided by the first power of the class of line bundle. So my notation tells me that this is A plus B tensor O of A plus B. Now, stop me when what I say is not clear or right, because I'm used to these notations, but the other thing was, this is an action, right? And this is O of A tensor O of B. So I can view this as A plus B tensor, I think I chose O of B, and then tensor of A. And this is A plus B, or 1 plus B, tensor O of A. I'm not sure that what I'm doing is the most efficient way to do it. Actually, I'm quite sure it's not. But it's kind of computation I find myself doing, and I did it this way, so it's fair if you see it done this way. So I have to say something about this term, a plus b over 1 plus b, high school algebra or elementary school algebra. So here I need this, I need to correct by that. I really feel I should apologize for the simple-mindedness of this. So forgive me. This is a, and what's left is 1 minus a times b over 1 plus b. Looks like I need one more line, but I have this whole board for me. Oops, don't exaggerate. So what was it? A plus b over 1 plus a plus b. This thing is equal to that. And this is equal to that. So this is a plus 1 minus a, b, 1 plus b, tensor of a. I think I'm one line from what I need. Tensor is, of course, linear, so this is the same as a tensor a, which is this. And this is an illustration of these properties. Now, you should view that as the Chern class of O minus a times a class. So the recipe is that after you balance it so that it pretends to have degree 0, you just bring the tensor in. Tensor by a, this is 1 minus a plus a. This 1 plus a down here is this term, if you're keeping track. And I apologize for pacing back and forth. And the rest is b over 1 plus b, tensor of a. Okay. As I say, this is not the most efficient way to go, but if I were doing this computation, I probably would do exactly these steps. Okay, this is where I was. This was the formula that would give me the Segre class of W. I had D union Y, I think. I hope you remember the notation because I kind of remember them and I don't want to rewrite them. But now that I have this way of thinking, this is precisely one of those. So what I have is pi plus star d or 1 plus pi plus star d. Please do check that I didn't make any mistake.
I'm just wondering the 1 minus e plus a over 1 plus a.
Yes, it's 1 minus a b over 1 plus b. This is the way I actually think. No, I have to correct it so that it has rank 0 because I don't want this guy. So I pretend that I'm dividing by a trivial, the Chern class of a trivial bundle. Then as I tensor by A, according to the formula, I have to tensor this by A and tensor this by A. So that's why this is what I get. Thanks. And I really want this to be as clear as possible. So this is no longer there. And what I've left is this e over 1 plus e tensor by O of pi plus star d. So I think you see what's happening. The projection formula tells me things I can apply here. Pi over star or some pi plus star stuff. And then this property over here, pi was a proper birational map, so I just need to tensor inside pi over star of e over 1 plus e, tensor of d, Oof. I'm so happy I'm through this. This was our problem. What's d over 1 plus d? It's the Segre class, right? D in d. And this is 1 over the Chern class of the normal bounded of d. What's pi lower star of e over 1 plus e? That's the Segre class of the other thing, which I called y, if I remember correctly. There we go. So this was the computation that led to now, it depends on the point of view. This is the same as the formula I put on the board, which I have erased in the meanwhile, the one with the volume coefficient. Precisely, with k, but I don't remember to, yes, there we go. You see why I want this? Because I don't have to remember what k means. Right? And I don't have to remember that it's negative d to the j or something like that. That thing is all embedded in this notation. And you've seen, the reason why I've shown you this manipulation is that it is really a calculus. Now, once you get used to this kind of operation, it's very very easy to perform these kind of operations. And read the terms of a given degree by the trick I showed you is also kind of easy. So this is my alternative for the formula that it goes under the name of residual intersection, I guess. I should use it. Okay, this was the situation. I mean, if you've forgotten the picture, this is the picture I try to sell you. Sorting is done. Okay. Questions? Comments? My time tells me that I have to sacrifice one thing. Maybe I can just point out that, in fact, if you like inventing notation, there's a good notation to invent over here. This is a really a twisting of this Segre class. I mean, and Stephen Kleiman and Anders Thorup have introduced a twist version of Segre class that would precisely be this term over here. So I don't remember your notation for it, but the notation I use is something like this. I was planning to spend a few minutes talking about that because the reason why this is kind of nice is that once you allow yourself the freedom to change one of these Segre classes by a line bundle, then you can reach a numerative interpretation of the result. For example, as you've seen from our computation, right, this class does not need to be effective. The Segre class of the Veronese was 1 minus 9h plus 51h squared. Well, if you twist it by something, then it will be guaranteed to be effective, and the coefficient will have an enumerative significance. So somehow this thing over here, to some extent, is better behaved than a Segre class. And it arises very naturally in this kind of context. There you go. That's a summary of something I was going to talk about. So if there are no questions, I will change the subject quite a bit. But please remember this for the next 15 minutes or so. Because I'll come back to this. I will want to use this again.
Do you have a reference for this operation?
Yeah, I've used it in. I mean, I have papers where I prove this stuff.
You had, a sequence of 3 or 5 lectures where you explain.
Oh, really? I have forgotten that. But one place where I certainly have them is a paper on IMRN from 1994, I think. Yeah, I detail those properties a little bit. I use them frequently, so if you open a random paper of mine, you're likely to.
I think it was
okay.
a lecture in Poland or somewhere.
All right.
Yes, exactly.
Yep, go talk about these things in there. Good to know.
It's actually very well written.
Oh, thank you.
It really teaches you how to use this. My students have been using it, and they are physicists, and they've been very good at playing with this.
He's right here.
There you go.
Anyway, So the last topic I wanted to cover in these 3 lectures, so now the 3rd lecture begins, so to speak, right? Was some comments on characteristic classes. So this was Chern classes for singular varieties. Of course, I mean, the theme of the lectures is Segre classes, so I want to see this as a Segre class at some point. And I have to make choices. Oh, maybe this is worth saying. So the theme is to find a way to associate a class to a variety. So I want some mechanism that we start with a variety, say compact complex. That, as I told you at the beginning, the hypotheses are always the ones you need for things to make sense and to be true. I don't want to. These can, in fact, be upgraded if you want. And I want to associate a class in the Char group of V in some nice coherent fashion. For example, I want that if V is non-singular, then the class should be the Chern class of the tangent bundle of V cap V. And we have seen an example earlier today. Example, I've learned that this class that I call Chern-Fuson class is one of these. But then Boyer asked me what the degree of this was, and I had to tell you it was the degree of something else. It was the Euler characteristic of something else. So I want to examine this, but if you want, one thing I want is a class that will satisfy some kind of Poincare-Hopf statement, that is the degree of its zero-dimensional component should be the Euler characteristic of V, not of something else. And it's a little bit of a longer story than we have time for, but as a motivating example for the definition, let's look at what happens if I consider V and W both non-singular, and the projection with projections from the product. Let me ask you what you can say about the Chern class of the product after you push it forward to, for example, the first factor. This is a nice, straightforward computation. Because the Chern class of the tangent to the product will be the direct sum of the pullbacks of the tangents. So what I can write over here is C of pi 1 upper star TV, C of pi 2 upper star TW, cap V cross W. The projection formula applies to give me this as C of TV, cap pi 1 lower star of C of pi 2 upper star of C of TW. And you see, this is kind of nice because the push forward clearly kills everything that ends up being in dimension higher than V. There's a V here. Right, this lands in V. So if I have terms that have dimension higher than V, they vanish. And the only term that is not of dimension higher than V in here is the top Chern class of TW. So in fact, I can put top here without changing anything. All the other terms are 0. What's the top Chern class of the tangent bundle of a non-singular variety? Compact. It gives you the Euler characteristic. So this is, in the end, this is just taking the Euler characteristic, topological Euler characteristic of W as a coefficient to C of TV cap V. Okay, this is a small motivational computation that tells me that if I have a way to push forward things so that they keep track of the Euler characteristic, then maybe I have a chance of producing a class that does what I want. not sure it's such a good motivation, but it's a computation that I wanted to do. So somehow, if you push forward the Chern class in a situation like this, somehow the order characteristic of the fibers comes up, shows up naturally. Well, there's a way to encode that into a functor. So V any variety that determines a group. I've been talking to Ivan Martin in the last few days, and we always call this C, right, as constructible functions. So let me try to call it C. CV, this is an abelian group. Its elements are very easy to describe. It's finite sums of coefficient from integers. W is, forget about the W over there, it's a new W. W are subvarieties of V, this is a finite sum. And this function is the indicator function on W, that is the function that is 1 for P in W and 0 for P not in W. And the W's are integers. So it's the free abelian group. On the information here is just information on a subvariety. This is a copy of the group of cycles, algebraic cycles in V. But you're viewing it as functions for some reasons. This is an abelian group. It seems kind of a stupid abelian group. You're just putting everything together. It's a free abelian group. It has no structure. What gives it structure is that it is a functor in the following sense. If you have V1 going to V2 proper map, F, then you can define a push forward from the group associated with V1 to the group associated with V2, and it's easy to define it. What do I need to do? This group is generated by these guys. So it's enough, since this is a group, to decide what this function should be. And it's supposed to be a function, so it's supposed to have a value for P in V2, so I have to decide what this number is. And if you want, in my mind, this is the motivation for that definition, if you want. This is the order characteristic of the fiber of P cap W, so the fiber in W over P. Now, in fact, this defines a functor. Other fact, of course, this defines a constructible function, so this is really, I'm being, what I'm telling you is correct. I'm not saying that this is necessarily totally straightforward, but it can be worked out. And by the way, I think that if you want to extend this theory to things that are not in characteristic 0, then you already run into trouble here. So this, for whatever reason, is a theory that is well adapted to characteristic 0. That is a functor. It's a functor from varieties, complex compact varieties, and proper maps to abelian groups. Do you know of any other functor from varieties with proper maps to abelian groups? Of course you do. It's this Chow business that we've played with. So I have two functors from this category to this category. And then it may be a natural question to compare those two functors. So there's a question. This question was floating around, I believe, at the end of the 60s, beginning of the 70s, where I've seen it in the literature is attributed to Deligne and Grothendieck. Does there exist a natural transformation from the functor C to the functor A lower star, such that, maybe let me call it C lower star, C as in Chern. This will be a generalization of the Chern class of the tangent bundle, because the normalization condition here is that if V is non-singular, then C lower star at V of the function 1 sub V is the Chern class of TV cap V. So this business is a way to formalize the action of choosing a specific element in the Chow group of V. You just choose a specific function. 1 is a very good function to choose. And use this functor to use that as a choice of a specific element in the Chow group. That was a question, and the answer is yes. The answer is a theorem by McPherson. I believe 74 on the Annals. This gives an explicit construction of this variety, of this natural transformation. This is also, and I should point out that this is a unique choice, and the fact that it is unique is a consequence of Hironaka's resolution of singularities, because you know the value at non-singular varieties and you know the behavior under push forward, so once you know it exists, it's necessarily unique. There's only one such gadget. That's one theorem. Another theorem, which I always want to point out, is that this is by Brasselet and Marie-Hélène Schwartz. This class agrees, well, which class? C lower star of 1 sub V. Now, I'm not assuming that V is non-singular. V could be anything. So in the non-singular case, I'm talking about the Chern class of the tangent bundle. Otherwise, I'm talking about a new class. This agrees in appropriate sense with a class introduced quite a bit earlier, around 1965, by Marie-Hélène Schwartz. So we should give credit to her for coming up with the right definition, in fact, before the question was posed, as far as I know. But the factorial point of view, I think, is the Lingworth and Dickey-McPherson's. Why would Marie-Hélène Schwartz be interested in this class? Because I believe she wanted to have a good Poincare for singular varieties, and once we know that all this is put together, we can do the following computation. Suppose that V is compact, map it to a point. This map is proper, so I can apply what this class is doing. I'm calling C constructible function, so the diagram I want to draw is this. C of V goes by push forward by kappa to C of a point. What are the constructible functions on a point? They are just a copy of Z definition, right? Which happens also to be the Chow group of the point. On the other hand, up here, I can go from CV to C a point, C of a point. C is functorial, and that maps down to, sorry. What I need here is A lower star of V. This is my new thing. And now I can go down because kappa is proper. Now, if you give me a W inside V, what happens if I follow 1W? 1W here, let's see, where should I send it? I should send it to C of star of 1W. Oof. What happens if you do this? Well, you pick up the degree, as Mboyo called it, the degree of the zero-dimensional component. The notation that most people use is an integral sign. So this is degree of zero-dimensional component. On the other hand, what is the image of 1 sub W through this part of the diagram?
Just so I can do one stack Paolo, I was talking about Fulton 1.4.
Thank you. Also, thank you for the moment of break, because I felt I was talking for 20 minutes running. Any question, any comment, any complaint? And this is a little dry as expositions go, right? But let's see if we are all awake. What should I put here? Well, I should apply this definition of functoriality, which is still here. Yes. The push forward is the Euler characteristic of a fiber. But the fiber is everything that there is, because I'm mapping to a point. So it is the Euler characteristic of W. Aha, this has to be equal to that. So if you want, this is some kind of singular Poincare-Hopf. This class, if I make a definition now, has the property that its degree is indeed the Euler characteristic. And the definition, there are different notations for this, but it seems that this has become more or less standard. CSM of the function 1 is defined to be C lower star of 1 sub W. And I've been kind of careful. By the definition, I should put this in the A Chow group of W. But in fact, as soon as I have W inside V, I can put this in the Chow group of V, and I want to do so. It's often convenient to push forward to some ambient space. So the notation is not too good because it's not remembering the ambient variety, but you'll forgive me for this. For example, in W, that would make sense. CSM stands for Chern, McPherson, and Schwartz, because after all, she did this work earlier. Okay. What else can we say about this class? It is a natural transformation in particular. It's nice homomorphism of groups as soon as you have chosen a specific variety. And this translates into this class having a nice inclusion-exclusion property. So if you have W1 and W2 both in side V, then CSM of W1 union W2. Well, that would be CSM of the indicator on W1, W2. And what is that? Well, it looks like it should be CSM of 1 W1 plus CSM of 1 W2. But oops, that counts the intersection twice, and you don't want to count it twice, so you have to take the intersection away. Sorry, I'm not using my notation very consistently. It's not important, but I think over there it was in start, but the end result is that this is indeed CSM of W1 plus CSM of W2 minus CSM of W1 intersection W2 once you push forward these classes to V, which is what I'm doing implicitly over there. So this looks like the kind of things you teach to discrete mathematics students, and you call it inclusion-exclusion, accounts for how the number of elements in a union of two sets behave. We just pick up the same property. This is compatible with this observation over here, because all your characteristics satisfies inclusion-exclusion. So it generalizes the kind of properties to classes defining a variety. Now, I had a couple of things I wanted to do. One thing I wanted to do is to give you a construction of these classes. I wanted to construct this for you. And if you know the story, you might find it a little strange, because the way McPherson does involves defining something called the local Euler obstruction, and the Chern mother class, which is a third candidate for a class that extends the... And of course, I was not going to do that. I was going to do something else. I was going to serve you with a simple observation. Maybe I'll do a short version of that, because I think it's very nice.
Can we just mention
Yes.
that the Chern mother class is actually the one that has the nice Functorial property?
This has a very nice Functorial property, right? By the way, I should have put on the board that natural transformation means that if F is a proper map, then this equals that. That's what natural transformation will imply. So that's the nicest possible Functorial property. But you're right, the mother's class also has very nice Functorial properties. In particular, it's preserved by projection in... yes, if you're in projective space, the Chern mother class of the projection of varieties, the push forward of the Chern mother class, and that makes it computable in many cases. Yeah, the mother class is a beautiful class. It's very worth studying, but I was kind of amused when I realized that you don't need to have that definition if you just want to define this object. So maybe I'll do just a small version of that. I propose that we compute the following. I have some room here. V is a variety, say non-singular. D is a divisor, just a hypersurface. Don't mean anything fancy. I propose that we compute CSM of V minus D. Or let me call U the complement of the divisor. I want to compute its Chern-Schwarz-Mann-Persson class. Why do I want to do that? Because it's high school algebra. So I back to where I feel halfway comfortable. What is this? This is this, right? V minus D. So it is really CSM of V minus CSM of D. Oops, I want my divisor to be non-singular as well. By normalization, I know what CSM of V is. It's C of TV cat V. By the same normalization, I know what CSM of D is. It's C of TD cat D. David is frowning again. You don't like this?
I don't like it when everything's smooth.
Okay, yes. It's boring, right? We are doing singularities here. We're not doing no singular stuff. Yes, I agree entirely. But actually, that's a very good comment. You know, I mean, the emphasis here was on singular varieties. The underlying message I'm trying to convey is that, in fact, that's just as good or bad as considering non-compact varieties. And here I'm putting my finger on the non-compactness. So this is an open set in a variety. If I took my definition in the child group of U, this would not be very interesting, right? If I can define the Chern-Schwarz-Mann-Persson class of affine plane, but it will live in the child group of the affine plane, which is not very interesting. While by sneakily putting it in some kind of compactification, then it becomes more interesting. I could ask for the Chern-Schwarz-Mann-Persson class of the affine plane in. I was doing this, and C of TV cap V is C of TV, maybe cap if you want, V. What is this? It's a Chern class of a divisor in V, so I need to divide by the normal bundle of V. That will give me the Chern class of D, and then apply to D. There's too many caps. I don't need all these caps. But, very complicated computation, right? This is C of TV. What's 1 minus D over 1 plus D? It's 1 over 1 plus D. Why am I telling you this? So exercise. This is the kind of things I would have maybe worked out if we had a few more minutes. I could do that, but I'll try a little harder. D is a non-singular variety. And you have D1 and D2 non-singular and intersecting with normal crossing, so such that D1 intersection D2 is also non-singular. And again, that U will be the complement of the union. Do exactly the same computation using the same sophisticated tools. You will find that CSM of U, maybe some of you can eyeball it if you don't know the answer. The answer is pretty. You see what you do, right? You would do a little computation with a slightly harder thing. It would be 1 minus D1 over 1 plus D1 minus D2 over 1 plus D2 plus D1, D2 over 1 plus D1 times 1 plus D2. That is a mess, but it's not a mess. It simplifies to this. Which is kind of pleasant. That's exercise number 1. Of course, exercise number 2 is to generalize it to arbitrarily many components. V is non-singular. D is a union of components. The I are non-singular. And D is normal crossings. which by my definition means that all possible intersections are non-singular of the right dimension. U is V minus D. Then the exercise is to prove that CSM of U is C of TV over this. That's childishly simple, right? But it is true. So you see, if you had to quickly construct McPherson's classes, you could do this. And now I'll make David happy because now V is singular. Okay? What's worrying you about the time?
No, it's, I'm seeing if this message that I got was important. It's not.
Ah. It was not the time, it was your Apple Watch. Okay, yes, I see. V is singular. Well, nothing prevents me from writing V as a disjoint union of locally closed subvarieties, UI. I want this, of course, to be a finite union, otherwise I will not be able to do anything. I want the UI to be non-singular, locally closed. I can do this in a zillion ways. If you give me a nice stratification, maybe I can use the strata, but I don't even need to do that. If I want to just throw in a point and take its complement, I can also do that. I can do this in a million ways. But then, you see, by the construction, CSM of V is the sum over I of the CSM of UI. So I just need to understand what this is, and that gives me a construction of that. So the task is, if U is locally closed, non-singular in V, what is CSM of U? And this is what it is, right? Because you can always reduce yourself to the situation. Take U, close it in V, then do a log resolution here, so that you have a copy of U in U tilde, such that the complement of U in U tilde is a divisor with normal crossing. And on singular components. Call this map whatever you want. V.
So what is U bar? That's a closure. U bar is the closure.
U bar is a closure, and this is a resolution of singularities.
Okay.
Sorry. Of U bar such that. Yes. And then there you go. The contribution that you will give to the Chern class of U by this computation which you have done as an exercise will be V lower star of C of T U tilde, that's the compactification of U, over product of I, 1 plus di, where these are the components of T. Okay, so if you believe McPherson's theorem, then you know that this is true, and this is a different point of view. You don't need to know about local abstractions or Chern classes to construct this class. This gives you computational tools. We've used this successfully to compute Chern-Schwarz-McPherson classes of Schubert cells, for example. Schubert varieties with Leonardo Michalcia, both in the Grassmannian and the arbitrary flag manifolds, even equivalently. No, this is really very convenient. Questions, comments?
Yeah, is this an effective way to calculate local weather obstructions?
I suppose that you could reverse engineer this.
Yeah.
Have you done this? Shipping Zhang has done computations of this sort, including the local abstraction, but maybe not of this particular kind. Let me point out that you may know what this class really is. Now, of course, your exercise and my silly computation made this appear out of nowhere, but in fact, there's a theorem. This is also to point out this beautiful work that I don't think has been recognized as much. This is by Xiaoliao. If you have, maybe I should use different notation, maybe not. D inside V. Over there, I have a divisor with normal crossings. V is non-singular. What I need from D is that it is free as a divisor, which means that its logarithmic cotangent is a locally free sheaf. That's not enough. You need some extra condition, and one way to do it, to explain it quickly, is locally quasi-homogeneous. There's a stronger condition that has to do with linear embedding of the Jacobian, but this is good enough. So, for example, normal crossing is one of these. Then, the CSM class of the complement of D is the Chern class of the tangent bundle, the logarithmic tangent bundle. And you probably recognize that this is exactly what this is. Logarithmic tangent bundle, I mean the dual of the logarithmic differentials. And you probably know that for divisors with normal crosses, this is computing exactly that. So that's a particular case of this, which is much deeper. Okay. Okay.
So Verdier, Gonzalez,
Berg.
Formulas, is that essentially what you have here?
I've never thought of that this way. Now, I'm not doing any Nash graph or anything. So, I don't know. That's a good point. There may be a relation. So there's a formula for
Verdier,
Gonzalez-Springberg.
it's in here.
There's a formula for the local abstraction, which is in terms of a Segre class computation and a Nash block.
If you don't have the Chern-Maller class to compare these things, you don't have another abstraction.
If you don't have the Chern-Maller class, you will not be able to recover it. Yeah. You have a system of equations, you need to have it. Yeah. But Steve is right in that there's a field that this more or less has to do with that, right? And that this might take the place of the tautological bundle in the Nash block, and this may become a Segre class computation. It looks like that. I agree with that. But it's not a Nash block. It doesn't need to be, and it doesn't need to have the property of a Nash block. Good. I'm down to one topic and 3 minutes, which is not very encouraging. But maybe I can advertise another high school computation that you could do if you wanted to do it. And the result, this would be a motivation for a formula which I find, again, kind of useful. So here's the situation in which I would be able to do the high school computation. You take x and y divisors, you know, again, non-singular hypersurfaces. Oh, maybe I can capitalize on this actually to do this quickly. Hypersurfaces in a non-singular V and x intersection y non-singular. We have seen this equation a moment ago. I just had different notation. So x union y is a normal crossing divisor. The picture I have in mind is the picture you have in mind, I'm sure. Right? X and y, x intersection y. What is the Chern-Schwarzman-Persson class of this gadget? So I was going to do a computation in the style of what we have just seen, but in fact I can at least cheat a little bit. After all, I've just computed the complement of this. Right? So now to be C of TV, 1 plus x, 1 plus y, cap x union y. Sorry, cap. Okay, so again, I'm being particularly sloppy, so this will end up in the child group of V, where it should, no, instead of a child group of X union Y, where it should, but this is the result. Just need to take 1 minus 1 over 1 plus x, 1 plus y, and this is something. I believe you get x plus y plus xy, 1 plus x, 1 plus y. By now you know I like this kind of mindless computations. So what can you learn out of this? Well, you can remember that we proved earlier today a formula for residual intersections, and try to apply it here. So I propose to make up a scheme for which I need a notation, and I probably want to stick to my notes. I'll let W be x union y, and I'll let WT be x union y thickened along x intersection y t times. What is t? T is some non-negative integer. What do I mean by this? Very literally, I mean that if, let's see, do I have, yeah, it looks like I'm in sight knot as decorating the chessboard. So by now my notation is not as efficient as it should be. I apologize. I'll change mine about notation because I don't want to deviate from my notes. Let me D will denote the divisor. D sub t will denote this. W will be x intersection y. And then I have the ideal of W. I take its tth power, and this defines a subscheme which I call T. Okay? So this is what reminds me of what's going on. I'm taking a certain subscheme of D, take a power of its ideal, and using that to define a non-reduced structure on this divisor. Okay, well, I can compute the Segre class of this D sub T. And if I can compute the Segre class, I can compute its Chern-Fulton class. Why can I compute it? Because I put on the board exactly a computation that was giving me the Segre class of, let's give it this, in which one component is a divisor. What do I need? Still need one ingredient, and I hope you can survive 5 more minutes of this because it looks like you will need them. What was the formula? Maybe I can even remember the formula. What is S dt v? It will be, what was it? You have it in your notes and I had it on the board. It was the Segre class of D in V, and then I had to divide by the Chern class of D, and multiply by the Segre class of WT, that's my notation today, in V, tensored by O of D. I think I remember this. This is what's supposed to be. So what is WT? What's the Segre class of that? Well, remember where it came from. I have W in V. If I want the Segre class of W, I will blow up V along W. I will have an exceptional divisor. If T is 1, this is just E minus E squared plus E cubed. If you paid attention, you know that the, oh my goodness, this is not good. My notations are not working very well. I apologize profusely. WT is the ideal of WT. Is the ideal of W. Sorry about that. As I say, my notation is not very consistent, but I think what I have on the board is all correct. This is true, that's true. So the effect of taking the tth power of the ideal will have the effect of multiplying this E by T. So this is TE minus t squared e squared plus dot dot. Okay. And let me cut the chase rather short. This is a class that makes sense. If t is greater than or equal to 0, this makes sense. It's a certain non-reduced scheme that has a futons class, and this computes the futons class. What I'm going to do is something formal. I have now a formula. I can plug in t equals -1. We cannot stop you from doing that. I can compute the Schoen, but you can actually, because you can tell me when your time is up, but do that. So what are we doing morally? Instead of thickening the scheme along its singularity, we are kind of formally removing the singularity from the scheme. Now, I've never been able to make this make any mathematical sense, but that should make it behave as if it were non-singular. And you apply this. That gives you C of TV, cap S of dV, 1 over C of D. This class, if t is -1, is exactly the dual of WV. You remember I had this other piece of notation here, dual, that's exactly what that is, tensor of D. And now what we don't have time for is the high school algebra. Because in this case, D is X union Y, W is X intersection Y, so I can do this computation. And magically, what you get is C of TV, X plus Y plus XY. I'm copying from over there. 1 plus X, 1 plus Y, cap V. So this brute force computation tells you that this is the Chern-Schwarzman-Persson class of D. Okay, let me highlight this somewhere. And then we'll be essentially done. We'll have a few comments, but then we'll be ready to stop. No, so what I just hinted at is the theorem, which does not require this hypothesis, of course. Take D, any hypersurface in a non-singular B. Let W be the scheme, what I call the singularity subscheme. If you have equations for D, then the singular locus is the vanishing of the partials locally. Well, those define an ideal, so some people call this the Jacobian ideal of the divisor, locally defined by the partials. And then the theorem is that the Chern-Schwarzman-Persson class of D equals Fulton's class of D minus 1, where this is the operation you've seen over there. So this is maybe mnemonic. The formula is still over there. It's C of TV cap Segre class of D in B, and then this not so friendly looking combination. I hope I didn't forget the C of TV. No, I haven't forgotten. Okay, so what the high school algebra will tell you is the right formula that works in total generality. There's no restriction on the hypersurface. In fact, this works even if D is multiple. It's really, no, it's a very... Okay, this I can only advertise. This was my justification for why something like this may be true. In this particular case, you can check it by hand. And I'm essentially done. What I would like to, maybe the last thing I would like to say before we have any questions, if you have any questions. This happens, right? You go to a workshop and the guy giving a talk says, and just last month I've proven that. No. And that's exactly the case here. No? For 25 years I wondered how I could get away from hypersurface. No, you really need a hypersurface to do this. But it's too bad, because I had a nice formula for the Chern-Schwarzman class of something in terms that then can be computed. Now this looks unfriendly, but my code in Macquarie 2 or Martin Helmer's code in Macquarie 2 can do this. So you can go to Macquarie 2 and type in an equation, and it will give you the Chern-Schwarzman class. And in fact, by inclusion-exclusion, you can do that for everything. But I wanted a conceptual formula that would give me the Chern-Schwarzman class of any subvariety or subscheme, any subvariety, as something that would involve a Segre class. Of a scheme obtained from the singularities of Z. Right here, the scheme that keeps track of the singularities of D is clearly this. It's the scheme defined by the partials. If you give me an arbitrary subvariety, is there a scheme that will know as much as this, so that a formula like this will give me the Chern-Strassmann-Persson class? Yes.
Are you assuming that D is globally defined by one equation?
No.
Then you have to add the local equation in the idea.
Because I forgot to write a singular scheme of D. So I'll view it as a subscheme of D, even if...
Okay.
Right. So you're absolutely right. If you want this to be a global definition, you need the equation of D, but that's because I'm thinking of this as a subscheme of D. Right. Well, I wanted the same package for arbitrary schemes. I looked for it for 25 years, and then I found it last week. That's the story. It's not last week, a couple of weeks ago. I will not rewrite the formula for the simple reason that the formula is so simple that I should have seen it 25 years ago. And if I show it to someone who knows what he's doing, he will reverse engineering the fact immediately. I mean,
Are you sure you don't want to just write it down?
No. For one thing, I have not written it down for myself in...
Are you going to talk about it Saturday or Sunday?
No. Yes, I mean, but it's a self-preservation. Until I write it down for myself and I really check that everything is as simple as I think it is, then I don't want to. But I want to advertise it as if it were done. So that's a little unfair, but I'm really very confident that the idea is so amazingly simple that the only explanation is mind controlled by alien beings. That's the only reason why I've not seen it before.
Well, then go home and figure it out.
Yes, you can. Now that you know that it is possible, it's much easier. Okay, so this can be done. All right, maybe I should stop here. This is a good time.
So do we have some questions?
Yeah, so when do you think we might look forward to seeing this in the archives, Frank?
As soon as I go back to Toronto and have...
You mean like within a month?
Yeah, I think so. It's really, I mean, it is very similar to this formula, but there are a few...
Don't say too much.
No, I don't. But one thing I discovered is that I was asking myself the wrong question. That is why I didn't see this before, because I really wanted a subscheme of Z. While the right scheme to look at is...
We get a lot of information here. So let me just say something. This computation is extremely useful. It's not often that you have results in intersection theory of this level that end up becoming mainstream in another field like in string theory. So we use these things to compute what they call the charge of the free brane. And this was a collaboration actually with Paolo. And it seems as if these are like little tricks, but it actually gives you power to actually compute important topological invariants. So I always want to encourage people to look into the computational side of intersection theory. Intersection theory is there to give like numbers, to give results, and not just like theorems. Sometimes you want to compute things. Yeah. Is there any other question or comment? So,
could you just say, I mean, I'm not asking for the results.
No.
Connected with some scheme defining the singular locus?
Yeah, it's, what is this? This is given by an idea with some generators. And rather than looking at a singular scheme here, look at the generators, the explicit generators, and see their dependence. For example, if you have, excuse me.
Are you sure you want to tell more about
Jerry,
it?
the movie comes out.
So, look, he doesn't have to say more. We have a lot of things in the kitchen. We will make him speak when the camera is off.
Anyway, yes.
Yes.
Really
Ice creams.
rouse the taste and the appetites of the viewers.
History in the making for the viewer. Okay, so let's thank Paolo again.
Okay.